from the beginning. Okay, so the respiratory system. Obviously, the primary organs of the respiratory system are going to be the lungs, which is what we're going to end up spending most of our time talking about. But that isn't the complete picture. We divide the respiratory system into the upper and lower respiratory tracts. And the dividing line there is the larynx. So anything that's below the larynx, which is the air tube, so to speak, that goes down into the lungs, we call that the lower respiratory tract. Anything above that is the upper respiratory tract. So the upper respiratory system, its job is to warm, filter, and humidify the air that we breathe. You know, as we'll see, the surface or the business end of the lungs, where oxygen and carbon dioxide go into and out of the blood, it has to be a very thin membrane and it has to be very moist. So that makes it sort of fragile, intrinsically. So the air that we breathe, we want to condition it, we want to modify it so that it's as gentle as possible to those delicate surfaces down in the lungs. So that is what the nose does, or the nasal cavity rather. So we'll talk about that. The pharynx is the sort of shared space between the digestive tract for eating and drinking and the respiratory tract for breathing. So that's, this area right here. And then we get into the larynx, which now you're into the lower respiratory tract. So we have the larynx. The trachea goes down through the chest, and then we get into bronchi, and we'll talk more about all these terms later on. But then we get down into the lungs, where we have huge numbers of these things called alveoli, which are sort of air sacs that have very thin walls and allow oxygen and carbon dioxide to move around. All right, so upper respiratory tract, lower respiratory tract. Another place that the distinction is made is at the clavicles. So, the clavicles determine upper versus lower. All right. So what does the respiratory system do? Well, obviously, its principal function is about what we call gas exchange. So all the cells in the body need oxygen. They all produce CO2 that we have to get rid of, lest our pH get lower and lower and our CO2s get higher and higher and we die. So that primary function is to provide an extensive surface area for gas exchange. So the way the lungs work is, in the end, air and blood are going to be brought very, very close together. Because if you bring those two things very close together with a very thin wall in between, the oxygen from the air can move into the blood, and the CO2 from the blood can move into the air that we then exhale. So the lungs provide that extensive surface area. Okay, so that's the principal function. In order for that to work, though, the air that's right next to the blood there, it has to keep being replaced, because we're adding CO2 to it and we're taking oxygen out of it. So to keep that air fresh, so to speak, we have to move air in and out of the lungs all the time. So that's what we typically call respiration, is the movement of air, or ventilation rather, moving air into and out. And we're going to talk about how that air moves next time, I think. All right, so there's that. Then we have protection. Because this membrane is very, very thin and wet, it's very fragile. So in order to prevent that membrane from breaking down, we have respiratory defenses. So one of the functions of the respiratory tract is to protect those very delicate surfaces from dehydration, temperature changes, environmental variations, changes in environment, hot, cold, dirty, clean, as well as defending against pathogens that might try to invade the lungs or the lungs tissues, or debris. As we, in the air that we breathe, there is not just gas molecules, right? There is stuff suspended in the air, dust, for example. Where does it come from? It comes from particulates that are suspended in the air. So the respiratory defenses have to have a mechanism for dealing with those contaminants or those particles that enter the lungs as well. So that's an important piece that we'll talk more about today. And then producing sounds. The respiratory tract is the driving force behind our ability to make sounds with our larynx, with our voice box. So speaking, singing, other forms of communication, all of those are powered by the lungs and the muscles of expiration that push air out of the lungs against resistance, like we'll talk more about next time. And then finally, the detection of olfactory stimuli. In the top of the nasal cavity is the olfactory epithelium, where we detect odor in a room or from food or whatever. And that system can't work if there isn't air moving through it all the time. So the respiratory system, in addition to producing sounds, it also facilitates the detection of stimuli, molecules in the air from a distance by moving air past that olfactory epithelium. All right. So a little bit about respiratory defense. So the deep tissues of the lungs, where the alveoli are, have very, very thin walls. So we need to keep stuff out of there. But if you look at the respiratory tract, it's a dead end, so to speak. It has only one entrance and exit, right? So everything that goes into the lungs has to go back out the same way, because there isn't another path out, at least not in terms of the air spaces. And given the fact that stuff is in the air other than oxygen and carbon dioxide, there has to be a system to trap those particulates so that our lungs, over the years of our life, don't just end up filled up with dust, so to speak. So one of the principal systems for that is what we call the mucociliary escalator, which I know sounds like a big, long term, but it's a pretty simple idea. So here what we're looking at in our picture is we've taken the side of the trachea here and we've zoomed in, right? So this is the epithelium, like you learned about last semester, right? The epithelium stands between the air, so this is where air is going in and coming out, and here, these are the deeper tissues, right? So between those two things stands an epithelium. And for the respiratory system, it's a columnar epithelium that is ciliated, so it has cilia along the top, and we call it pseudostratified because when we look at it under the microscope, these new cells here make it look like there's layers, even though there's not. So a little refresher, pseudostratified columnar epithelium. Well, along the surface of that epithelium, and this is the luminal surface, so here's the air space, we have a coating of mucus. And that mucus is actually produced on purpose, even though sometimes we think of it as just a bother. It's made all the time, and it's made on purpose. And it's made by these cells right here that are interspersed between the epithelial cells. We call these goblet cells. And the reason they got their name is they look a little bit like a wine goblet. So the base would be here, this would be the stem, and this would be the actual wine glass part, right? So they look a little bit like a wine glass. Goblet cells. And they produce mucus. That mucus is put out here on the surface. Mucus is sticky. So as air moves past or through this tube right here, dust, particles, anything that isn't a true gas, part of the air itself, ends up getting trapped in this mucus, right? So that it cleans the air. Like we have a filter in our furnace or air conditioning system. Well, one way you could build a better filter is to actually spray a bunch of sticky stuff on the filter, and it will trap stuff from the air, or pull stuff out of the air, because the gas molecules are not affected by sticky, but solid molecules are, so they'll end up getting stuck in it. All right, so now we've got debris stuck in the mucus. Well, what happens then? Well, again, the lungs are a dead end. So this mucus, it can't just stay there. So it's got to move. The reason that these epithelial cells have cilia on their surfaces is to move this mucus lining all the time. So mucus is always being moved towards the esophagus, towards the opening of the the food tube that goes to the stomach. So for the lower respiratory tract, mucus is always being moved up, and for the upper respiratory tract, it's usually being moved down, right? And the reason for that is this mucus is going to end up in the digestive tract where it can be digested and destroyed, essentially. So, yes, we cough, we sneeze, we blow our nose, we eject mucus in that way, but the vast majority of mucus is handled by basically swallowing it. The digestive tract takes over and then destroys it and recovers, any nutrients there that are remain to be grabbed. So we call this the mucus escalator. So it traps debris and then it moves it up and into the digestive tract where it can then be removed, destroyed and removed from the body. All right. So it's part of the respiratory defenses. Now this is just one, but it's the one that your book talks about. The respiratory tract has some others that we'll talk about as we get a little further on. All right. So the respiratory epithelium, pseudostratified ciliated columnar epithelium. It's the only place in the body that you have this. If you hear on a test or something, pseudostratified ciliated columnar, you know you're talking about the respiratory tract because there isn't another place where you're going to find that. So pronounced goblet cells, tall, skinny cells that have cilia at the top. These cilia, they move, they beat, kind of like rowers in a boat that are, multiple rowers in one boat. They sort of all beat together. Well, the cilia do that same thing. They beat to move that mucus lining up towards the esophagus. All right. So respiratory epithelium. So we find the typical respiratory epithelium. We find it in the nasal cavity. We find it in the trachea. We find it in the larger tubes, bronchi, what they have called, that lead into the deeper regions of the lung. The only place we have something different is in the space shared by the respiratory tract and the digestive tract. So the pharynx, we're going to talk about the pharynx in 2 chapters, this one and then the digestive tract. So it's the region behind the mouth, okay? So here's the nasal cavity up here, and then here's the oral cavity. So behind the oral cavity is the pharynx. And because the pharynx deals with both food, liquid, and air, it has a different epithelium. It has a stratified squamous epithelium on it instead. So here the epithelium is a little different. But then we get into the trachea that goes back to our friend pseudostratified. And then when the tubes get very, very small, we're going to see that the lungs are arranged a lot like a tree is, where you have large trunks that give out large branches, and then the branches get smaller and smaller as you go towards the end, right? Well, when you get towards the end of the tree system, the epithelium starts to become cuboidal. It starts to get smaller, essentially. And then when we get to the very end, they're flat, so they're squamous epithelial cells. And now these are type 1 pneumocytes, which we'll talk more about later on. All right. So the nasal cavity is, at least for me anyway, it's always a little difficult to visualize the nasal cavity. We think of the nose as the thing that sticks out from the front of our face, the thing that holds up our glasses. But the truth of the matter is the nasal cavity extends a significant distance behind the nose. So the nose is really just the front or the door to the nasal cavity, which, I'm going to back up, which in reality is sort of box-shaped, right? So this is all nasal cavity. So a lot of the region that we think is brain actually isn't in our heads. The nasal cavity makes up a significant portion of the skull's size or mass. And so we have this great big giant nasal cavity. So as long as your mouth is, right, the nasal cavity goes that far back. So just to help you sort of visualize that. And here in the front, this is what we think of as the nose. So you can see it's really just the front door to a much larger room, so to speak. So in this picture, which is sort of a bizarre picture, but what we've looked at, or what has been done is, here's the skull, or here's the head, and we've taken this section of coronal plane, this is called, so we're coming down the side. And the reason that this, elaborate picture was done is to show you these structures right here. So you see these little curlicue type things? Those are what are called the nasal conchae. And essentially, they're little swirls almost. There's 3 of them on each side, a superior, a middle, and an inferior. And essentially what they do is they swirl the air. So as you guys are breathing through your nose right now, as the air comes in, because of these conchae, the air is swirled around a bit before it goes down into the lungs. And the reason for that is to extend the amount of time that the air in your nasal cavity is in contact with the mucosa that lines all of these surfaces here. Because the nasal cavity's job is to filter, in other words, take debris out, warm, increase the temperature, and then humidify the air that you breathe. So when you're breathing through your nose, by the time air gets down to your lungs, it's at body temperature, it's at close to 100% humidity, and most of the particulates have been removed from it. So, the nasal cavity does those functions. It's why when you have a cold and you can't breathe through your nose, you end up breathing through your mouth, and your mouth gets dry, and you have to, you end up drinking more and all those things. It's because when you breathe through your mouth, you're not getting the benefit of that air conditioning, the conditioning of the air going down in. Now, we also exhale through our noses, and that too has a reason. Because as the air passes then back out through the nose, some of the moisture is recovered, the temperature is recovered, so that warmth is brought back into the system, so that like on a cold day, the air coming out through your nose is not as warm as body temperature, because by going back out through the nose, that heat is removed then, and so it can be salvaged. So the nasal cavity plays an important role in conditioning the air. And then also another thing you can see in this picture are the maxillary sinuses, which remember last semester we talked about sinuses in the skull. This is a great picture of them, because you can see they're great big huge things that sit just inferior to the eyeball there. All right.
There's 3 pairs of conchae.
Yes, there's a superior, a middle, and an inferior on both sides. Yep. All right. And whenever you see pictures of the nasal cavity, the conchae, you don't see them. They just look like bumps. But these bumps have a complex shape. They actually are swirl shaped, as we saw in that other picture. All right. All right, so nasal cavity. So here is the nose sticking out here. This is what we call the external nares, which is the entryway to the nasal cavity. There are coarse hairs in the external nares, and again, it's a filtration system. Why do we have hair in our nose? It isn't just to annoy; it's to keep large particles out of the nasal cavity. Also, insects. It keeps insects out too, which I think we're thankful for that, right? All right, so that's the external nares. At the back of this box-shaped nasal cavity are the internal nares, or nares. And that's where air then can exit the nasal cavity and head down into the lungs, into the larynx. So behind the nasal cavity is the region of the pharynx called the nasopharynx. All right, so this whole piece right here is all pharynx. And so the common name, I think, for this is the throat, right? Well, the throat's proper name is the pharynx. So the nasopharynx is up top. Here's that the adenoids, the pharyngeal tonsils that we talked about, right, are right here. This is the opening to the eustachian tube that goes up to the ear that we talked about in the special senses chapter last semester. All right, so nasopharynx. Oropharynx is the region of the pharynx behind the oral cavity, right here. And then the laryngopharynx is the region of the pharynx that is behind the larynx, which is right here. And the larynx is the first part of the of the lower respiratory tract, right? So nasopharynx, oropharynx, laryngopharynx. All right. An important thing to note here is, okay, so in the back, this is the esophagus right here. So when you swallow food or drink, it's going to go through the mouth and it's going to head sort of down the back. All right. So the esophagus is posterior. Air makes sort of a turn to the front, right? And, you know, if you think about this, that makes sense in terms of an arrangement. Because air, you know, gas can go around curves very easily, right? Solids and liquids, not so much. You know, it's hard to guide a bicycle around a very sharp bend, right? So what evolved is because air can make this sharp turn, the larynx is in the front. But because liquids and solids coming in can't, the esophagus is in the back. Because you can imagine if you're swallowing something, it's just going to sort of fall right here, right, into the esophagus. And we're going to talk about the swallowing reflex when we get to the digestive tract. But one of the things that happens is this flap of cartilage right here, when you swallow, it gets pushed down. So like, it's like this, and when you swallow, it goes like this. So it essentially blocks the air tube so that food can go past it and down into the esophagus instead of into the lungs where you really don't want it.
So when people aspirate, is that just when that cartilage isn't working?
No, aspiration is just food or liquid has gone in here instead. So it doesn't mean that this isn't working, it just didn't work that time or something. Or there's lots of causes for aspiration, but that cartilage bit is just one. Yeah. All right. Okay, so moving down into the lower respiratory tract, the larynx or larynx, depending on how you want to say it, is this is commonly called the voice box, and it begins essentially at the hyoid bone, which you can palpate, but it can be difficult. But it's the hyoid bone is up high, just underneath the mandible, and then below it is the laryngeal prominence of the thyroid cartilage, also called the Adam's apple. So a lot of you can make a note on this slide that there's not very much of this anatomy that I want you to know. Okay, I want you to know the thyroid cartilage, the cricoid cartilage, and then these two ligaments. So the things in boxes, those are the things I want you to know, not all of these other labels, right? So the epiglottis is that cartilage flap. This is the epiglottis right here, right? So in our picture where the soft tissues have been taken away, that's the epiglottis, that's the hyoid bone. This is the thyroid cartilage. It gets its name because it sits just underneath the thyroid gland, right? And it is shield-shaped, is how it's typically described, and it comes to a point in the front. And that point is typically referred to as the Adam's apple. All right. And then the next cartilage down, the first cartilage of the trachea, is a sort of thick, round cartilage called the cricoid cartilage. So that's right here. From the back, it looks even bigger, which is right here. Okay? And here's that epiglottis from the side. Here's the epiglottis looking at it from the back. Okay? So we have these important cartilages. Now, crossing, so this is the windpipe, right? The trachea right here. Well, crossing the windpipe from front to back are two ligaments that literally cross the space. So if you were to look down at the top of this structure, you know, here's the tube, that's the trachea, and these ligaments cross the space from front to back, all right? And I'll show you in a minute how those ligaments then create what we call the glottis, which is where the sound of the voice is made. All right, so know the three main cartilages and their anatomy, and then those two ligaments. All right. So if we put the soft tissues back in, what we're doing here is we're looking down the trachea. Okay, so if you've ever seen an intubation where a breathing tube is put in, this is the view they're looking for, right? Because what they want to do is they want to put that plastic tube into the top of the trachea so that, you know, you can give air to the patient. Okay, so this view is that view. So epiglottis, this is this is the front of the patient. Anterior is down here. Posterior is down here. So those ligaments that cross the larynx, they are attached to muscles and cartilages that kind of have a little pivot mechanism to it. So it means that these ligaments can move. They can come together and close off the glottis. This is what we call the glottis, the opening to the trachea, or they can open and allow air through. So one of the other ways we prevent aspiration or food or drink down the windpipe is whenever we swallow, the glottis closes so that food or drink can't get down into the lungs. It's one of the reasons why you can't talk and swallow at the same time, because when you are swallowing, the tube to the lungs is closed, so air can't come out. All right, so it makes a kind of gate. So this is the vestibular fold that makes up most of the gate. But then at its edge is the vocal fold. The vocal fold is what vibrates to create sound or create the phonation in our voices. And it vibrates because when air is pushed through this closed glottis, the folds vibrate. So if you've ever played like a wind instrument where you had to blow through something to make sound, well, our voices work in that same way. Air is pushed through pushed through a thing that causes that thing to vibrate, and then that vibration we hear as sound. All right, so kind of like a gate. Okay, and then I have a cool video to show you. Okay, so what does that look like? So we've got ligaments, vocal folds. Okay, so when we look at the beginning of our movie here, so here's the vestibular folds, right? Here are the vocal folds. Here's the opening between them, that is the glottis. And what we're going to see is, we're going to put these in motion, I hope. Why is that not playing? Wait, I'm going to back it up.
Some young female vocal cords during a stroboscopic exam.
All right, so those are the vocal cords moving. Now pay attention that when she takes a breath, look at what happens to the glottis. All right, so vestibular folds, vocal folds. It's not in sync, but that was a breath. When it went like that. All right, enough of that. That's weird. It's not in sync. The audio and video are not matching up. So you saw them vibrate, right? Yeah. So that's how when you're singing and talking, that's how it happens. And then it's a cool mechanism in the body because it has this pivot to it. So now when she takes a breath in, obviously you want to have plenty of space for air to go, right? So the vocal folds go like this and they open into this kind of V and allow air to pass much more easily through it. All right, so the glottis. All right, so today's anatomy day in terms of respiratory tract. A lot of anatomy, and then next time we'll start putting things in motion. But, okay. So from underneath the larynx, then, you get into the trachea. The trachea is very simple. I mean, it's essentially a tube that brings air from the top of the larynx down into the lungs. Now, the tracheal cartilages, when you look at this picture, you might think that they're circular, but they're not. They're C-shaped, so they look like this. So what we're looking at there is the front. So the front is rounded, as you can feel in your own neck. You can feel your trachea. It feels round. Well, at the back, it's not round. So behind the trachea is the esophagus, right? The tube that's going to bring food down into the stomach. So the back wall of the trachea is not hard. It's actually soft. So these cartilage rings that we see are only present in the front. At the back, there is no cartilage. And the reason for that is so that as we swallow, the esophagus has to get a little bigger as food passes through it, right? So because the back wall of the trachea is floppy instead of hard like the front wall, it can bend forward as we swallow stuff along the back. So the back wall is flexible to allow food to pass through the esophagus, which is directly behind it. All right. So why have cartilage there at all? Well, because of how we breathe, which is, air flows in because we reduce the pressure in our chests to make the air flow in. If we didn't have these cartilage rings in our trachea, as soon as we went to take a breath, our air pipe would collapse and we wouldn't be able to breathe. So the reason that the air tubes of the lungs all have these cartilages is because they have to be propped open. Because otherwise, if you took a breath, they would have a tendency to collapse in on themselves. All right. Okay, so then we get down into the lungs. All right, so from the trachea, we have a primary branch point, which is right here, right? So we have one trachea that then splits into a right and left primary bronchus. The spot where they split, we call that the carina. So C-A-R-I-N-A. The carina is where the left and right main stem bronchi or primary bronchi head to the lungs. And then from there, the tubes that bring air into the lungs follow the exact same pattern as a tree does. So, when you look at a tree, you have one trunk and then you have some big branches, right? Well, in the lungs, there are two branches. There's the left main stem and the right main stem. And then each of those branches. It creates more branches, but those branches are smaller. So the first branch is the primary bronchus, so that's here. And then that branch branches. So now we have secondary bronchi, which are right here. Secondary bronchi go to each lobe. So a primary bronchus goes to each lung. A secondary bronchus goes to each lobe of the lung. We're going to talk about the lobes later on. And then there are more branches. So the tertiary bronchi now go to what's called a bronchopulmonary segment. But there are tertiary, quaternary, so on and so on and so on. Until eventually you get to the twigs, right? Twigs have leaves. Well, the twigs in the lungs are the bronchioles. Okay, so these are the twigs. And then the leaves of the tree are the alveoli. So these tiny little bronchioles have alveoli that stick off of them, essentially. So just like the leaves of a tree. Why the similarity between trees and lungs? Because essentially the two things are doing the same thing. A tree survives or lives by having huge amounts of surface area with gas, with the air. The lungs do the same thing. They want to have a huge amount of surface area. So, it's just one of those spots where nature did the same thing in two very different organisms because it had to accomplish the same goal, which is to have a huge surface area for gas exchange. All right, so the primary, secondary, and tertiary bronchi, they all have cartilage in their walls, as you can see here, these plates. Now, they're not complete. In the trachea, we have these nice C-shaped rings all the way down. But in the when the bronchi get smaller, the rings aren't complete anymore. They're more like little struts or plates on the side. Until we get down into the bronchioles. Bronchioles don't have cartilage anymore. They're too small, essentially, to have cartilage. And in some ways, bronchioles and arterioles share a lot of things in common. They're very similar structures. The arteriole, of course, has blood in it, and the bronchiole, of course, has air in it. That's the difference. So they don't have cartilage, but they do have smooth muscle in their walls. So just like an arteriole can change its size, a bronchiole can change its size too. So it can get larger or it can get smaller. And before class, we were talking a little bit about asthma. The restriction of airflow that comes along with asthma is because of bronchioles. The bronchioles are too small. They stay too small all the time. And because they're too small, they resist the flow of air through them. So like when we give albuterol, which is an asthma medicine, what it does is it makes bronchioles relax. So it makes bronchioles bronchodilate or get a little bit bigger. And when they get bigger, air can pass more easily through them and then into the alveoli. So the bronchiole is one of the more clinically relevant spots in the respiratory system because of the effects of asthma. So when bronchioles get too small, that means air can't get to the alveoli, and it's the alveoli where the work gets done. So there's a blockade, so to speak. All right. Steroids help to reduce the inflammation that is triggering the bronchioles to be too small.
So it's not that they're just contracted, it's just, why are they so small?
Asthma in the end is an immune, hyperactive immune response. So essentially, the body thinks that there's something toxic or caustic that's trying to enter the lungs. So, what would be the intelligent response to that? We'll clamp everything down, right? But in the case of asthma, there isn't actually anything, there's no threat. The body's just behaving like there is. So one approach is you get the bronchioles to relax, but that's a short-term solution. In the end, you want to turn the immune system down so that the bronchioles won't be contracted in the first place. Does that make sense? All right, so the bronchioles. So they change size. And why do they change size? There is a logical reason for it. The lungs, just like everything else in the body, you want to conserve resources that are hard to find. So when we're like you guys, when you're just quietly breathing, your bronchioles are quite small because that way you're not losing excess water all the time through your exhalation. And another is in defense. If you walk into around a swimming pool, where there's a lot of chlorine smell, you might find it gets a little harder to breathe. It's because your bronchioles just went like this. They got smaller to try to protect the alveoli from those caustic fumes. So it is a good thing that bronchioles can change size, even though it goes wrong in asthma. All right. So this is the bronchial tree. It's kind of a cool picture. Certainly nothing really to learn off this, but you can see how the left and right main stem, and then the secondary bronchi go to each lobe here. So boom, boom, and boom. And then on this side we have just upper and lower. So just like the branches of a tree. All right. So the lungs have lobes. Each lobe is provided air by a secondary bronchus. We have a right lung and a left lung. They're not the same. One of those rare cases of asymmetry in the body. So the right lung has 3 lobes, superior, middle, and inferior. And because it has 3 lobes, it has 2 fissures. Fissures separate lobes, right? So the right lung has a horizontal fissure separating the superior from the middle here, and then it has an oblique fissure here. So this is all anatomy you should definitely know, because this is pretty simple, straightforward. You should know lobes of the lung and stuff like that. All right. On the left side, we just have a superior and an inferior, so we have 2 lobes and 1 fissure. And in here, it's the oblique fissure. So where did the middle lobe go for the left lung? It disappeared because there needed to be room for the heart. So the left lung shares the left chest with the heart, so it had to give up its middle lobe for there to be room. And I think we talked a little bit about as humans evolved and our chests got wider and flatter in terms of front to back, the heart had to rotate to the left. Well, when it did so, there was no longer room for a 3rd lobe in the left lung. Not that it matters. We have more lung than we need. You can actually live on just 1 lung. So, so we have that cardiac notch is what we call that. The space that would have been middle lobe that's now occupied by the heart. We call that the cardiac notch. All right. So this is the anterior and posterior, this is looking at the lungs from the side, essentially, this picture is. If we look at the lungs from the middle, we see this grouping of structures in the center. That's a hilum. You know, we talked about a hilum when we talked about lymph nodes last time, and we're going to see hilum in other places, and this is one of those places. A hilum is just a place where things go in and come out, all in a cluster. So if we look at the right lung, in the hilum, you're going to find three things. You're going to find air tubes, bronchi. You're going to find arteries, and you're going to find veins. Because those are the things that are going into and coming out of the lungs, right? Blood is going into the lungs to pick up oxygen. That's the arteries. Blood is coming out of the lungs, carrying oxygen to the rest of the body. Those are the veins. And then the bronchi are going to carry air in and out. So when we look at the hilum, what we see is here are the bronchi, right here. Here is the pulmonary artery, so this is the artery. And then there are always two veins. And that's an easy way to sort of remember what's in the hilum is there's two veins, one artery, and then air pipes, right? So that's the right lung. On the left lung, here's the artery, so pulmonary artery, two veins again, and then the air pipe, sort of in the center. So we have our hilum. Now this other, I want you to know the fissures, I want you to know the lobes. I'm not interested in you knowing like the diaphragmatic groove and all that kind of stuff. So lobes and fissures, and then what's in the hilum, right? Okay, good. We can get to some questions. All right. Functions of the nasal cavity include all of the following except what? Whoa, that's weird. Did you get the question? Yes?
Trying to log on. Yeah.
Oh. I got a very weird screen for whatever reason. All right. I have no idea what you all answered because my thing messed up, but you have to think through this one. So let's go through each answer. Okay, so filtering the air, we talked about that. So yes. Humidifying the air, that's what the conchi help to do. Swirl the air, add water. So in addition to the swirling effect, I don't know if I mentioned this, but the nasal cavity has a very rich blood supply. So you take lots of blood together with lots of air moving past it, and you're going to get humidification and warming. So C, yes. So what about D or E? Okay, so D, acting as a resonating chamber in speech. Now we didn't talk about that, but if any of you have had a cold, does your voice change? Like, do you sound different with a cold? Yes, you do. And it's because the nasal cavity does act as a resonance chamber. So just like a guitar, you know, if you plug up all the holes, or and play it, it sounds different. Same thing. So the one thing, when you cough, you typically don't cough through your nose, right? So it's going to be hard for E to be the case, and so E is the one that doesn't belong. All right. The portion of the nasopharynx, or the pharynx, sorry, that receives both air and food is which of those? All right, got 4 answers, so jump in there. Let's see people. All right, best answer, B, oropharynx. Could you make a case for C? Yeah, you kind of could, because food does pass through the laryngopharynx, but oropharynx there is your best answer. All right. Hold on, I want to see where we're at. Oh, not too bad. Okay. Okay, so the tree system, we've got primary bronchus, secondary bronchus, tertiary bronchus, and then we get down to the bronchioles. So the bronchioles are the twigs, right? And the alveoli are the leaves. Well, the whole purpose of the respiratory system is what we call gas exchange. So oxygen coming into blood, carbon dioxide going from blood to air. Well, in all of this part, so from the trachea to the primary, secondary, tertiary, all these pieces here, the walls of these tubes are too thick for gas exchange to happen. In other words, there's too much tissue between air and blood to have any meaningful oxygen or carbon dioxide movement. So we call those the conducting portions of the system, because all they do is move air. They don't actually participate in the movement of oxygen and carbon dioxide. Until you get down to here, which at the bronchial level, the respiratory bronchioles, and it's just like a tree. Okay, so if you think twigs are bronchioles, right? Leaves have stems, typically, right? And the stems are very, very thin and small compared to the twigs that they're growing out of. That's a respiratory bronchiole, is the stem of a leaf. And its walls are thin enough where oxygen and carbon dioxide can start to move from blood to air and vice versa. So that we call the respiratory portion. So the respiratory portion of the respiratory system is the respiratory bronchioles, the stem of the leaf, and the alveoli, the leaves themselves. All of these other tubes are part of the conducting portion. All right, and we'll talk a little bit more about what that means when we get into the physiology parts. All right. So what if we add everything back together? Okay, so we've just been looking at the air tubes so far. This is now putting the other pieces together. Okay, so following those branches of the bronchi are arteries and veins, right? Because the lungs' purpose is to put air next to blood. So air comes in through the bronchial tree, but where does the blood come from? It comes in through the pulmonary arteries. And the pulmonary arteries sort of follow the bronchi out into the leaves, so to speak. So here's a branch of the pulmonary artery. Here's a bronchiole, and then, so this is a twig. We've zoomed in, right? You can see the bronchiole has lots of smooth muscle in its walls. And now we start to get into leaves. So these are alveoli. They're sort of sphere-shaped bags of air that have very, very thin walls. And then wrapped around all those alveoli are massive amounts of capillaries. Because what we want is we want to take blood and put it right next to air so that oxygen and carbon dioxide can move. So the blood has come from the pulmonary artery, and then it's going to go back to the heart through the pulmonary vein, which is here. The pulmonary veins don't follow the bronchi on their way out. They sort of take a different path back to the heart. So we have artery, bronchiole, and then we have alveoli. And that's where we're going to stop for today. So we'll pick up with the lower respiratory tract anatomy then next time.